Hi, I'm Ben from the University of Edinburgh, the Centre for Fire Safety Engineering, and today I'm going to be talking to you about a smart way of modelling heat and smoke movement through complex buildings. I'll start off by talking about fire risk in complex buildings, walk you through the current method of modelling buildings in the fire safety industry, and juxtapose the risks and the current method to find out where our missing pieces are and where there might be unaddressed risks, which will lead into my project, which I'm 1.5 years into, which is aims to address these outstanding risks, which is coupled modelling. What causes fire fatalities? And that's obviously a very, very big, wide question. We could be thinking about occupant characteristics, things like age, mobility, familiarity with a building. We can also think about the actual material of the building itself, building linings. One thing we do know, and one thing that's present throughout fire fatalities, for example, in the building here, which is in Hong Kong, the Gali building, where sadly 40 people lost their life, is 65% of all fire fatalities are due to smoke inhalation. And 50% of fire fatalities in the UK, the US, and in Australia are caused outside or occur outside of the room of fire origin. So it's in areas remote from the seat of the fire, the location of fire ignition. So we know that the majority of deaths are caused by smoke, and they're caused far away from, or at least 50% of them are caused in the far field. Leads on to another question: what causes that spread and growth of the fire and the smoke? Again, another very big question. We could be thinking about active fire suppression systems, the fuel itself, obviously, ventilation systems. And again, one thing that sits over all of that and caused massive fire spread in this building here, which was First Interstate Bank in the US, which caused $50 million worth of damage, is building itself, or more specifically, the total building system. So elements like stair shafts and lift shafts and risers and active ventilation systems and doors which can open and close throughout the duration of the fire, windows that can break. So, do we address these hazards? We know that fatalities are caused by primarily smoke and in the far field, and the total building system drives this fire spread and this smoke spread. So there's a two-way coupling, a two-way bidirectional coupling between the fire and the building. The total building system affects the fire and smoke spreads throughout the building. Let's walk through a typical analysis, a fire safety engineering analysis of a building here. This is De Rotterdam in Rotterdam. So as a fire safety engineer, we're going to use our Primo tool in the fire safety toolkit, which is a three-dimensional computational fluid dynamics, because we need to look at the time evolution of fire safety or life safety criteria such as visibility, temperature, toxicity. So we have an issue on the 30th story. So the first thing we do is cut off 31 and above and 29 and below. And we know that the issue occurs in a room in the middle of the building, and it's related to two of the exits. So we cut off everything else other than our room of fire origin, maybe a connected corridor or two and a couple of exits. And you might be looking at me and saying, you've just said that the total building system affects how fire grows and how smoke spreads, and smoke spreads throughout the building, and remote from the fire origin is 50% of fire fatalities. Why do we curtail the domain in such a manner? And it's because the computational fluid dynamics models are so computationally intensive. Millions and millions of calculations for every second of simulation time, and we might be needing 2,000 seconds of simulation time or something like that. And then obviously the conclusion is what is the risk embodied in curtailing, so heavily curtailing our building. And when we make our fire safety engineering requirements and we define our design and we expand it out to the entire building, what phenomena are we ignoring? And ultimately, we don't really know. So what's the potential solution? And it is hybrid modeling, a smart way of modeling a building. So we start off with, this is our three-dimensional computational fluid dynamics model. And in here, we're solving a form of the Navier-Stokes conservation equation. So we're conserving numerically mass and species, energy or enthalpy, momentum, and there's combustion modeling in there as well, and heat transfer modeling. So instead of curtailing our domain there, what we can do is expand our boundary conditions and include a much simpler model, for example, a one-dimensional network model, which is formed of ducts and nodes, which we can use to represent the total building system, shafts, stairs, other stories, risers, doors opening and closing. And in this much simpler model, we're still carrying out conservation equations, but the numerical or the computational load is, orders of magnitude lower than for the 3D CFD model. So we're still conserving mass, energy, momentum, and unsteady variables also. And then at the interface, we couple the two models together into the overall hybrid coupled model by inside in each submodel, modeling pressure boundaries and mass flux boundaries and enthalpy flow boundaries also. As with any simulation tool, we need to provide model evaluation. And that comes in two flavors, one being verification, one being validation. Verification is the checking that the implemented numerics are, the numerics that you've coded up are correctly implemented. Essentially, it's checking the math. And validation is checking whether the correctly implemented numerics can, within reasonable limits, accurately predict real-world phenomena. Essentially, it's checking the physics. So that's what I did for my hybrid model. And for verification, it starts out with a very simple 3D domain, as you can see on the screen there, and also a one-dimensional network model coupled into this 3D domain. And you isolate each numerical solver and I compared the output of my results with first principles. For example, and I'm not going to go through the detail, but mass conservation, transport time throughout the domain, pressure differentials at various locations in the domain, and energy conservation. After you verify the numerics of the code, you move on to validation, and this is where I am currently actually. So I'm in the process of designing a set of experiments which I'll both use to validate my hybrid model, but also to experimentally examine the effect of a total building system on the fire, the bidirectional two-way coupling of the total building system and a fire. And it might look something like this. So I need to make sure that my boundary conditions are very tightly controlled. It's a medium-size experiment which we can fit under our hood in Edinburgh. And that's where I am right now. I'm in the stage of designing this experiment. So the implementation of the hybrid model, once I've finished the validation, actually from an impact point of view, my hybrid model is now part of the fire dynamic simulation piece of software, which is the most used CFD tool in the industry. So it might look something like this. We go back to our building, and it's the same issue, the same fire safety issue that we want to look at, same location. So again, we'll curtail 31 and above, 29 and below, and we'll curtail down to our room of fire origin and a handful of enclosures. Next, what we do is couple in our 1D network model. So we start to explicitly model the total building system now. And each one of these lines might represent a lift shaft with a lift going up and down, or a ventilation shaft, or a stairway, a stair pressurization system. Then when we make our assessment and we define our fire safety design and expand it back out to the building, at least we've explicitly considered the total building system, so we can have more confidence about how we predicted the fire is going to spread, grow, and how smoke is going to affect the rest of the building remote from the fire origin. In conclusion, what we've done is considered the building system, the total building system, whilst still remaining within a reasonable time frame as expected by the multidisciplinary team and the construction industry. Thank you very much.
Thank you.